get the notice, yes, there is no problem. Okay. So in future, this is where that retail, finance, health, everywhere it is going on. Okay. So now let me go into what happened. Okay. So now good health and well-being, you can see that AI is used extensively in health sector. AI-based pathology predicts origin of cancers of unknown primary. These are all the news articles, publications from not normal journals. It's a very high impact factor journals. You can see that it's published in Nature. Okay, so it's a, you can see that AI is coming in scientific things. Breast cancer spotting AI pathology tool, it is helping the doctors today that what is the level of cancer, progression of cancer, etc., etc. You can see AI is used in helping drug discovery with respect to your COVID also. And then you can see that AI is used everywhere. So this slide is extremely important for all the faculty members and students. Please pay attention. You can see that recently in silico medicine initiate first human study. It is in silico medicine. There is absolutely no experiment. It is purely computer based. In silico medicine is a company which uses AI for drug discovery. That company recently initiated first human study, whatever the number which you understand much better, a novel drug discovered using in silico proprietary end-to-end artificial intelligence platform. Okay, so now it is no longer a myth. It is no longer a hope. No, it is already a reality. FDA approved drugs were discovered by in silico medicine, and now eventually you will have, you can, maybe it will be labeled AI powered drug. Okay, so maybe a personalized medicine developed by AI. Okay, so it is no longer a myth, it is no longer a hope, it is already a reality. So $60 million were invested on this company just because of this one news. Okay, so you can see 60 million means 450 crores in Indian rupees. So we need something like this in India also. Okay, so this is a awareness presentation. You can see that AI is no longer a textbook. AI for drug discovery is no longer a textbook message. It is a reality. Okay. Please understand the drug discovery. When you say drug is a small molecule, it's a cluster of atoms. Spatial arrangement of atoms is a drug. Now, how this in silico medicine come up with development of novel small molecules as leads, and then eventually it become drugs. So I strongly encourage each one of you to go into internet, search for in silico medicine, then you study the story, then you will get some confidence. This is just awareness meeting presentation where AI is, you can next 10 years, you can also contribute. You can also start, you can help the students to come up with some startups. They will be coming up with Indian AI powered drug discovery for Indian diseases. I want to read that one in the future. So it's all in your hand, how to encourage the students to do AI for drug discovery as a pharmaceutical faculty. Okay, so now I want to little bit go, maybe it was too fast, I was talking excited. So let me slow down little bit. So now let me go into the details. What is AI? So especially in chemistry context, I am going to talk about. So AI in chemistry, biology, and medicine, you can say, which I mentioned in the beginning of my presentation, that I was inspired by Professor A.J. Corey during my master's degree. So Corey reagent, Corey reaction, etc. we used to study. So now when I became a PhD student, I got so much fascinated. So I saw this article in Science, which was published in 1960 or 70s. Okay, so that is how I started writing the article. What he mentioned is computer assisted design of complex organic synthesis, but what I converted was AI for chemical synthesis, because AI is something beyond simple computer assisted design. Okay, then eventually he became a Nobel laureate in 1990. So you can see that he's the one who used computer for chemistry. Okay, so in future there may be so many Nobel laureates who will be supported by AI. We never know in future. There are several textbooks are now written artificial intelligence in drug discovery. Research papers are written in Future Medicine Chemistry, which I'm citing here. Nathan Brown, he published a lot of articles and publications. He compiled a textbook on artificial intelligence drug discovery. So I strongly recommend, please go through the in details. It will be very useful. It should be become a curriculum. It should be UGC approved syllabus in pharmaceutical curriculum in future. Otherwise, we will be left behind. Okay, so I strongly recommend all the academicians participating this meeting. Please try to include this as one of the component. Maybe 8 years, 10 years from now, the student coming out of the pharmaceutical background will have a better knowledge about this. Okay, so I strongly recommend, because I can't do it, but teachers can do this. Okay, so now you can see in newspaper, people are talking about AI for drug discovery. They talk about this, lock and key mechanism, etc., etc. So traditionally, a medicinal chemist knows what functional group should present in a molecule to be a drug. Today, because the number of data, the amount of data, volume of data is huge, it's very difficult humanly to look into each and every molecule from natural sources and then synthetic sources, and see the functional groups or fragments responsible for bioactivity. It is extremely easy for a computer, since you represented the chemical structure in computers in proper format. The computer can understand what are the functional group should present or absent that is responsible for particular selected activity with respect to disease of interest. Okay, so now you have complex problems. There is a chemical structure which is complex, and there is a disease, type of diseases, the human factor, many things are complex. Now the computer will find the correlation between the molecular fragment responsible for either increase in activity or decrease in activity. That's all AI is all about. Once you understand the fundamentals of the functional group responsible for bioactivity, then it is easy for the computer to design a new molecule with desired characteristics. It will eliminate the toxic part. It will eliminate the side effect part. It will eliminate all the other problematic part in a molecule. It will try to do in silico design of a novel molecule using de novo approach based on what it learned over a period of time from different literature, different relationship between molecule and bioactivity. Now it will be able to design. This is where AI play an important role. So the traditional versus modern drug discovery, now you know very well. Okay, so role of AI in healthcare. Okay. Leave it. Okay, I'm sorry. Okay, so now I just want to give you a break, and if someone want to unmute yourself and want to ask some questions, maybe 1 minute or so we can spend on it. So Raja Ram, can you tell the participants if they have any doubt about this?
Yes, sir. Yes, sir. Dear participants, any yes, question or any clarification you can ask.
It's almost 1 hour, so now
yes,
I will be going practical part of the AI for drug discovery. I can continue, no problem. You can put your questions in the chat box if you want.
Okay, sir.
Okay, so let us continue. Then if participants has any questions, please put into the chat box. Okay, so now let us go into the technical details. So now one word about sustainable development goal. Everybody's talking about sustainable development goal and AI. There are sustainable development goals. There are 17 goals are there, out of which the goal number 3 is good health and well-being. It is defined by United Nations. So now it is compulsory for every country in the world to take care of their citizens, their health, their well-being. Okay, so now today we are talking about pollution. There should be no pollution. There should be a clean water. There is no poverty. There should be no poverty. There is a good education. So these are all the some of the sustainable goal defined by United Nations. Okay, one of the goal is good health and well-being. Now, when it comes to role of AI in healthcare, it helps in several ways: detection, early detection, improving the decision making, help in treatment, medical services, I mean, several stages, including your end of life care. Okay, so there are several decision making, diagnosis, keeping well. You can see these are all the case studies where you can see that it helps. So now, having said all these things, now let us go into the how AI will actually develop a drug. How a But this is the conventional route for drug discovery and development. What is the route? What is the pathway for development of a drug? So it involves the identification of disease, which includes isolate proteins and etc. Then find the drug effective against disease protein, and then preclinical testing. So then formulation, human clinical trial, scale up, etc., etc., and then finally FDA approval. So when you look into the technology space, so there is a genomics, proteomics, biopharmaceuticals, and high throughput screening and virtual screening. So this I will restrict my discussion AI for drug discovery in this only three stages. What are the three stages? Once the disease is identified and the isolated protein, okay, you have a PDB database where you have access to all the 1,70,000 or 80,000 proteins today available in PDB public domain. All the disease related proteins, because of COVID, so much data now flowing into the public domain. And then there is a huge collection of molecular data in public domain. If you ask me where I can download the molecule, you can download happily 1.130 million molecules. I repeat, 130 million molecules, close to 13 crore of molecule from PubChem. Okay, then that means you got a molecular diversity. Second step, among these 13 crore molecule, how many are biologically active? Then you got to go to Chembel database, where each molecule associated with particular protein or disease of interest is already linked. So this become an input for AI to find the relationship between bioactivity and molecular structure. Okay, this is where the technology comes. When you come to in silico company, in silico drug discovery company, in silico medicine, when they discovered the clinical data, they are going. That means they are processing 130 million 130 million available known chemicals in at least in the electronic format against the all type of diseases and activity data available in Campbell, for example. So this became a knowledge base. Based on that, they discover a molecule which is not yet reported. Okay. So what are the technology they use? Genomics, high throughput screening, virtual screening, combinatorial chemistry, molecular modeling. I don't want to go into details because it's all very well established. Now let us go into specifically for AI in drug discovery. What are the components involved in AI in drug discovery? So it starts from target selection, compound screening, preclinical trial, cellular and genetic target evaluation, genomic and proteome analysis, bioinformatics analysis, high throughput screening, structure activity relationship, in silico studies, etc. So when you look at the small molecule as a drug, developing a drug model means model drug properties for the disease of interest. This is very, very important. It is linking the drug means atomic level properties with physical, chemical, biological properties of the molecule. Then they design molecules that meets the drug properties. First, you understand what are the drug properties. Then, what are the molecular features responsible for correlating with the drug properties. Then the computer has so many algorithms, AI algorithms, that can link your relationship between atomic and molecular level. So then new chemical entity for disease of interest, chemical data. The one important component today people are using extensively is called NLP, natural language processing. What is natural language processing? When you write a manuscript, you say that compound A tested on that particular cell line and found active, and the GI50, growth inhibition factor 50, is value so and so. This is what you written in the abstract or publication or the part of the manuscript. Now computer don't want that beautiful grammatical English language. It has to eliminate all the things, get only two parameters. What is the molecular data and what is the bioactivity data, on which context? That's all. So to extract, that means it has to eliminate all the unnecessary things which is required for modeling. So what is necessary things to be extracted from huge, if you written 40-page article, something it has to take only 4 or 5 parameters from that 40-page text line. So this is where one option is you can go download the publications, highlight that 5 parameters with highlighter, and then give to the student, make them to do Excel sheet. Okay, it is laborious process. One paper you can do, 2 paper you can do, 10 paper you can do. What about the 35,000 journals with high frequency of publications on the topic of interest? So how it is only possible, it is humanly impossible, it is possible only through computers. That is where this natural language processing comes into picture. Natural language processing is easy for reading the political news or Twitter news, etc. But when it comes to molecular data, recognizing a chemical name from a text is very complex, because chemical structures are represented by a common name, trade name, IUPAC name, CAS registry number. Which one it should recognize as a chemical? So that's very, very challenging. Chemical text mining is most complex things. So we have worked on that and we developed some, I will come into the details. So how to recognize a chemical name as a chemical structure, valid chemical structure, and extract the chemical name and convert the chemical name automatically into a chemical structure. And once you convert the chemical structure, then you have to generate some molecular features that is related to these biological activities. That is where AI comes into picture. So then you do the structure activity relationship. Once you recognize the chemical structure, then only you can relate with the bioactivity of interest. Once you understand chemical structure, you can also do the docking studies, molecular dynamic studies, etc., etc. Some books. Okay, so I will answer all these questions. Okay, fine. So let us continue this. Keep putting in the chat box all the questions. I will come into the end of the presentation. So now you can see that what I'm talking about is already, review. There are several review articles are coming today. I stopped, thinking about writing a, quick article because everybody is publishing. I want to publish, which should be practical. It should be helpful. Each and every student at the BSc or BPharm level should be able to follow and be able to reproduce what is published. These are all theory anybody can write. So I stopped thinking about publishing something uncooked, unprocessed. Okay, so we are working on practical application or practical way of implementing AI in drug discovery platform. But for understanding, I strongly encourage all the participants to go through these articles, these and related articles which is being published. This is published in Cell Press. It's a very high impact factor journal article. So advancing drug discovery via artificial intelligence, very relevant to our topic of interest. And then this is a textbook or a book recently published by Royal Society of Chemistry. You can see that artificial intelligence drug discovery. So this, when it's already available in publications and it is available in book format, why it cannot be made as a course material? Why UGC should not make this one as a course material? This is my question. So if you have to survive and sustain, and if you have to perform and compete with the world, it is early adoption of this field in our curriculum is very, very important. Okay, so now already we discussed about sorry, okay, kindly mute yourself, later we will discuss. Okay, so representative pipeline in drug discovery is already mentioned. I kindly request you to go through this particular article so that you will get more insight into how really AI helping in drug discovery. So this is standard procedure. The molecular collection, if it's accessible, the main problem is the relevant data. Molecule is available, activity is available, but molecule with activity is not available. So you have to find the resource where molecule and activity with citing a reference, which journal it was published, what is the supporting material, whether it is reproducible. That information is not linked and available. It's very expensive to access it. Okay, only some huge pharmaceutical companies can access that information. So once that data is available, for example, primary assay high throughput data is available, which molecule is active against which cell line, that data is available, then you can go for structure activity relationship. Once you go for a structure activity relationship, then you can find the functional group responsible for R1, R2, R3, responsible for bioactivity. Then you can go to the design and then you can make a virtual molecule and do the docking studies, then find the binding affinity, etc., etc. Then you can go for chemical synthesis. Again, you can go for clinical testing in vitro, in vivo, and then again it is a continuous process. So don't think that okay, I developed a drug, end of story. No, it is a continuous process. There is a continuous improvement is required in AI. Otherwise, you can't learn. So there, this I want to introduce three terminology. What is AI? AI is a big circle under which you have two component, big machine learning. Under machine learning, there is a deep learning. In simple terms, machine learning is a supervised learning and deep learning is a unsupervised learning. So there is no bias in unsupervised learning. Supervised learning means you are instructing the machine, this is way you have to learn. Whereas in unsupervised learning, it learns by internally and make the model. So now you know there is a AI, machine learning, and deep learning. These three terminologies you know. All the information is available in that article which I mentioned. Okay. Now, how to start with? There are so many open source tools available for drug discovery, AI-based computational tools available for drug discovery in a open domain. So if you are a computer programmer, you can directly download and test it, or you can tell your students, the young generation who are very young people at the age of their 24s and 28, they can quickly grasp and they will be able to do. So we are very busy with our daily schedule, but whereas the students can spend their time productively, instead of getting into games and other things, they can get into learning something, then they can contribute significantly. It all depends upon us, how we motivate the younger generation to go into these open source tools and data, build something which can become a solution for future problems, future diseases. So there are so many people already put efforts to develop these tools. It is time for us to look, and instead of reinventing the wheel, better use the existing tools and customize them to meet your requirement. This is my suggestion. That's why I always try to promote open source tools and open data for drug discovery. So let us now, we have only half an hour to go. So I will quickly go through why cancer, why it is very important. In addition to pandemic, cancer also, very big disease. You can see the trend is keep on alarmingly increasing. You can see India is not left behind, but unfortunately, this data is very old data up to 2005. But I want to show you only the increasing the trend. Basically, it is increasing. Sometimes the data is not publicly available because cancer is a disease. People don't want to tell they have cancer because they feel, because of the societal things, they don't want to disclose that they have cancer because of psychological reasons. So then automatically the data gets suppressed. Then automatically that action taken to be, action is not properly taken. Okay, so this is the breast cancer incidences in the world, and this is the death rate. So the reason, you can see that even though the prevalence of cancer is very high in America, the death is compared to Africa or these Asian, these Arabian countries. But when you go into the death rate, so you can see it is less death in developed countries, whereas mortality rate is very high in these African and other countries. Okay, so you can see that developed countries, even though prevalence is very high, but the death rate is very low because they take precaution, they give the solution, early detection, early cure. Okay, so now it is cancer. I don't want to educate the faculties here. Cancer is a very complex disease, and then there are several targets involved in several type of cancer, and then there is a pathway mechanism involved in signaling pathways involved in cancer. Then we need to develop several type of inhibitors. What type of inhibitors? That cancer anti-cancer agents are inhibitors, that JAK inhibitors, SRC kinase inhibitors. So there are several type of inhibitors needs to be developed because each pathway has a specific route. So we have to inhibit at the pathway level. Then this is a very complex, treating cancer is a very complex process because there are several pathways involved, several target involved in curing the cancer. So then people treat the cancer with surgery, removal of solid tumors. They use radiation to kill the cancer cell. Actually, here I want to mention that identifying cancer at the early stage is very, very important. So now they are talking about circulating cancer cell lines, tumor cell tumors, circulating tumor cell lines. So that means tumor cells. So this is very important topic. Even several, even in India, scientist, student from NCL become a entrepreneur. He developed the technologies to early detection of cancer from a circulating cancer cells. Okay, so this is then you can quantitatively identify, qualitatively identify that cancer. Accordingly, you can take a prevention and precaution and treatment. Okay, so then one early detection is very important. Once it reached a very large final stage, so it is very difficult to treat. So early detection, and then, or in case if it is already too much, then solid removal, radiation, chemotherapy. We will talk about chemotherapy as then anti-neoplastic agents, etc. in this topic of interest. How to develop the anti-neoplastic agents. Okay, so then cancer means it is supposed to kill the cells, specifically the cancer cells, not the normal cells. So identifying the molecules which is very specific to cancers and not to the normal cells, that is very, very important. This is where AI can come into pictures. All the information with respect to treatment of patient, how the molecule interact with the patient, what is the good effect and bad effect, if it is captured properly, this will help you to design a drug with specificity, selectivity, and even promiscuity. Okay, so now, for example, let us start with anti-cancer drug discovery context where a lot of information is available. These are the list of drugs. These are the mode of action. This is the indication or the cancer for which these molecules are used as a treatment. This information goes to the computers. So we create a cancer drug profile. What is the chemical? What is the output of this particular chemical with respect to cancer? So there are people know that this data goes into the computers. So once the data goes, now we have to convert the data into a knowledge. So the data measurement, calculation, bioactivity goes into the computer, which is the base of the pyramid. And then we try to link the bioactivity with respect to chemical structure. That is the context. So we are converting data into information. And once the chemical is linked to a context, bioactivity context, then you generalize the functional group for responsible for bioactivity. This is the knowledge you generate. This is called inductive learning in cheminformatics, where huge data is there and then information is there, then knowledge is generated. This knowledge, AI generate that knowledge, it become a model. That model is used to predict the bioactivity data for a novel molecule. This is very simple procedure. Convert data into knowledge and apply the knowledge, AI knowledge, for predicting the new drug with expected bioactivity. So for example, today, what data we can get it? So you can look into the textbook Introduction to Anti-Cancer Drug Development, where all the cell lines, for example, leukemia, non-small cell lung cancer, colon cancer, prostate cancer, then breast cancer. So each cancer, there are 10 types of cancer, and then 10 type of cancer has a different type of cell lines. And then we have to find out the molecular response to these cell lines. So a single molecule, you take it and apply, test it on all the cell lines of all the cancer types, then you get some outcome. This should go into the computers. Luckily, people, National Cancer Institute and NIH, National Institute of Health, did this type of studies, screening the compound against the cell lines. The data is available in public domain. If it is not available today, I won't be talking about this topic, because without data, what mesh modeling we can do it. Okay, so this data is available. This is a very, very important data to start the anti-cancer drug discovery program. So I also encourage two topics. One, Introduction to Anti-Cancer Drug Development book. You can get access to it and then go through the anti-cancer drug development details. And then another book I recommend is The Principle of Anti-Cancer Drug Development. This is another book where they also talk about these cell lines and the response with respect to molecule of interest, the concentration at which the cancer percentage of growth reduced. Okay, so this is what very important. Then you can see that okay, I hope it is not chat for me. Okay, so then you can see that how the progression or reduction in cancer because of the chemical activity, biological activity of the chemicals. Okay, so I'll skip some of the basic slides. Uh, Now you are convinced that there is a data, the machine is going to learn, and then it is going to apply that data. I'll skip. So you learn from the experiment, then you design the next experiment. So you learn from molecule and bioactivity relationship. Now you can design the drugs. So now AI also helps to avoid animal testing. Earlier I mentioned that MSDS data sheet where we extracted lakhs and lakhs of chemical structures along with bioactivity toxicity data. We found that the molecule tested on rat, rabbit, dogs, etc. are already available. Now, can we use the existing data to avoid killing these animals in the future? So because of the animal rights, many things, we don't want cruelty to animal, etc. We don't want cruelty to animal. So we have to use the computer power to learn from uh, historic data. So already the molecules are tested against these organisms. Then now you don't need to kill them. Use the data, because then find the chemicals structure and feature response relationship with the toxicity. Apply that toxicity data to predict the toxicity for the new chemical. So now this is approved by FDA also. Computer predicted toxicity is approved for FDA drugs. Okay, FDA it's also approved because of it is reliable nowadays. It is reproducible. People talk about BBB, blood-brain barrier, etc. Okay, so 1 second. Okay, so we can use AI for reducing the animal testing. Now let us go into the technical part of how AI understand the chemical structure relation with respect to bioactivity. This is what I am going to stress upon. This is where cheminformatics comes into picture. Once you have a chemical structure which is linked to physical property like melting point, chemical property like solubility, biological activity like growth inhibition factor or toxicity, IC50, TC50, TD50, etc. Now this is chemical structure is now linked. Now once the chemical structure is known, we know that how to synthesize. Once you know the chemical structure, you can also do structure elucidation. So for example, IR, NMR, mass spectrometry, you can use it for recognition of chemical structure from the extracted or synthesized compound. This structure elucidation is possible. Now you can also find out, given the chemical structure, how to synthesize it, what is the source, from where it came from, how to synthesize that molecule, how to convert the molecule into a new molecule. So this is comes under reaction prediction. Okay, then you can come up with what is the material responsible for synthesizing that compound using a chemical reaction. Given a chemical reaction, you can also know how to do the synthesis using retrosynthetic analysis, that is called synthesis planning. So AI is helping in all the domains, in QSPR, in property prediction, QSAR for activity prediction, and QSPR means QSTR for toxicity prediction, and also synthetic route prediction. So let us look into one molecule. Say, for example, Taxol. So Taxol is tested. It can be used for experimentally measuring the chemical properties like pKa, log P, solubility, stability, etc. Experimentally, you can measure the chemical properties. And also Taxol can be tested against biological activity, against particular biological activity, toxicity, biotransformation, pharmacokinetics. You can actually experimentally measure the biological properties. These are the two properties. What is shown in the right hand side is experimentally measured. But then I am going to talk about the intrinsic properties, which is called molecular descriptors. You are describing the molecule. Mathematically, you can calculate the molar volume, connectivity indices, molecular weight, composition of atoms and bonds, etc. You can calculate molecular weight, polar surface area. So there is a right hand side, which is shown as a chemical properties and biological properties, which is experimentally measured. What is shown in the left hand side is a intrinsic properties or a molecular descriptor, which can be calculated given a chemical structure. Okay, now what computer is going to do, what AI is going to do is correlating what is in the left hand side with the right hand side. That means intrinsic properties can be correlated by the computer to predict the properties of log p, solubility, stability, etc. Similarly, using the intrinsic properties, you will be able to predict the properties of biological activities like toxicity, biotransformation, activity, anything. Okay, so this is what computer is learning from the literature data. It identified the chemical with the chemical properties and biological activity. Then it is try to mathematically calculate the intrinsic properties, what is shown in the left hand side, and then it is try to predict the right hand side. So it from the literature, it correlate the it extract the information of experimental data, and after learning it is predicting the experimental data using the intrinsic properties. This is the core component of a machine learning or AI or deep learning. People can tell any terminology, but this is the fundamental. Without calculating the intrinsic properties or understanding the molecule at the atomic level, it is not possible to predict the chemical properties. It is not a magic. Okay, so first you have to understand molecule at the atomic level, at the two-dimensional level, three-dimensional level, whether it's aromatic, aliphatic, whether it is the what is the molecular volume, what are the charges around this molecule. The reason is opposite charge attracts, right? So if you have a target in a biological context, if you have a target or a protein where it has a binding site, this molecule should go and bind. If the molecule is neutral, it is not having any charge, it will not go and bind, right? So this is what computer understand. Opposite charge attracts, so it has to find the opposite charge to for getting a better binding. So it has to calculate the intrinsic property, it has to understand many properties to find the better molecule. So people have some wrong conception. Computer, you draw the molecule, you get the bioactivity. No, there is a lot of process involved inside the computer behind the screen. You cannot calculate the physical, chemical, biological properties from the chemical structure. You know that, no, sir, you are wrong. I have used the ChemDraw. I draw one molecule, I click one button, I saw NMR spectroscopy, I calculated the melting point, boiling point. I don't know what you are telling. You may be telling lies. No, actually, what you are seeing is correct. Uh, you may be thinking that one click, the answer came. But behind the screen, they don't show you the process in which they generated the NMR spectra. They don't show the process in which they predicted the melting point, boiling point of the or bioactivity of the compound. They don't show because it is not relevant for the newcomer. But whereas for an expert, he knows how the values comes out. It comes through uh, uh, calculating the intrinsic properties, correlating with mathematical models, and then it predicts the property. Then only you know how accurate it is, like what I shown in the melting point prediction in the earlier part of my presentation. Okay, so you are learning from the experimental bioactive activity. You make the context with the chemical structure, then you make the generalization. That is how you are able to predict the structure, predict the property of the molecule of interest. So this is a structure activity relationship. So you have a structure, you can't directly predict the properties as shown in the slide. You need to convert into a 2D, 3D, then calculate the intrinsic properties called molecular descriptor and use the machine learning, deep learning to predict the properties. There are several open source tools from which you can calculate the intrinsic properties or molecular descriptor called chemical development kit, Padel descriptors. So the molecular descriptors or intrinsic properties can be constitutional molecular descriptors, topological, physical, chemical, quantum chemical, electrostatic. Depending upon the your requirement, you can select what type of descriptor is meeting your requirement. Okay, so there are several type of descriptors available. You don't need to calculate all of them. What is relevant with respect to your context needs to be calculated. Once it is calculated, then it can make a model. Once you have the model using algorithms like genetic algorithm, neural network, principal component regression, etc., you will be able to predict the experimental or things, etc. So this is I already mentioned to you. So you have a chemical structure, you have melting point. Now you are able to predict the melting point of novel molecules. So then to get the data, primary data, you have to do the text mining, manually searching a chemical information from a, this was happened in 1940s, 50s, 60s. People used to do, go to chemical abstract service, find the data. Today, you can click with the SciFinder and other things. I'm going to show you, if time permits, how we extracted the data from the SciFinder and used the data for building the mathematical model and build the properties. You can do it. If I can do it, you can do it. Okay, so this actually extract the chemical information, molecular data, physicochemical properties from the literature, and use cheminformatics tools to correlate the chemical structure and properties and build the models. So what type of information you can extract from the literature? You can extract the gene, protein, drug, disease information. You can build the biological network, how the drugs are related to your disease of interest using proteins and genes. Once you build the gene, protein, drug interactions, then you can try to bind the similar molecules in the target of interest, which is related to particular disease. This is all whole story all about. Once you understand, then you can design. Okay, so this is very, very important. Computer, when you say AI, it actually understand the relationship between molecule and activity. That is why it is able to predict. So what are the steps involved in structure activity relationship? I don't want to go into the lecturing about what is QSIR. Basically, you have a compound, you have a molecular descriptor calculated, we called out intrinsic properties, and then build the mathematical equations and then validate. So from where you get the molecules in public domain, it's a huge big data is available. Binding DB talking about 0.6 million relationship. Campbell talking about 1.7 million. That means 1.7 million molecules. 1 million means 10 lakhs compounds. Okay, so that much bioactivity is available. E molecule talking about 17 million. Your PubChem is talking about 94 million. Actually, it is more than 100 million today. That so much open data is available. Now you have to find the magic bullet. You have to find the $1 million drug from this collection. Then you can use this AI to do that. Okay, so huge data is available. Now finding the molecule of interest with respect to disease of interest is a challenge. So you manually it is impossible. So that's why we take help of computers to do these things. So there are we use some academic and commercial softwares which is cost effective. Now previously it used to be free for academics, so now because of the so many reasons it is becoming charged. This is our best tool because it helps in parallelizing the technologies. It is helping the distributed computing. It is a very low cost solution, so that you can run in 20 computers, 20 servers simultaneously. You can screen millions of compounds using this technology. Whereas when you buy one commercial software, only that is one computer only based on that IP, based on that computer configuration, only one computer it will run. It will not run in any other computers. So if you want multiple computers, you have to pay multiple times. Whereas this type of technology, you can run at the institutional level. There is no limit for running the licenses within the institutional level. Okay, so that's why we recommend or we use these open source tools along with these cost effective technologies for handling huge collection of molecules. You can't do with normal commercial software this type of data handling. Okay, they have some restriction. Whereas if you use this type of softwares, which is very, very useful. And then we last 15 years I am using this software for developing our open source tools. Whatever the publication which we did, whether it's a publication, patent, or journal article, book chapter, everything we used this type of tools, open source tools. So we use these tools to generate molecular descriptor, what type of descriptor, what type of equations we have to build. So we calculate the descriptor using the open source tools. We use the mathematical model using open source tools, and then we develop integration. So finally, at the end of the day, we put the compound which is not yet synthesized to the AI model, so that we know which molecule to synthesize. Why? Because it has a predicted biological activity of interest to our research. So what is the workflow? There is a compound, then you calculate the intrinsic properties using some softwares or open source tools. Then you build the initial QSAR model as is shown here. Okay, you have a list of compounds which I've shown you. So there are the compounds coming from any source. You have a list of compounds. So in this particular case, Campbell, it also has a bioactivity. Take that molecule, data and molecule. and compound selection with bioactivity. Then you calculate the molecular descriptor. You can use any of these tools to calculate the molecular descriptors. Once you have the compound and descriptor, then you can use mathematical models, which you can use open source tools, AI models, whether it is a PCR, PLS, ANN, KNN. There are several models are there. Okay, SVR, support vector machine, support vector regression, whether it's a binary method, whether it's a regression method. Then there is a LSTM, there is a GRU. There are so many deep learning methods where unsupervised models are available. So you have both supervised model and unsupervised QSAR model. Once you have that, you are validating. How you validate? The molecule which you model which reproduce the experimental data is a good model. If you are not able to reproduce, there is a large deviation between the experimental and predicted value, then that is not a good model. Then what you do? So you try to add or remove the descriptor which you selected for building the initial QSR model, and then refine the mathematical expression, so that one in a supervised model you can refine mathematical expression. In an unsupervised model, the computer itself will refine the mathematical expression. This is where the deep learning will help to refine the mathematical expression. Again, it is validating refined model. So it is a circular process. So until unless you are able to reproduce the experimental data, this is a continuous process. Once you are able to reproduce to some extent that experimental data, some minimum deviation, say for example in melting point prediction, if the compound is supposed to melt at 178 degrees Celsius and my prediction is 175 or 179, it is fine. But in the range of 14 degrees Celsius to 400 degrees Celsius, if I am able to predict with plus or minus 2-degree variation, that is the best model. That is what we presented in the journal article. It was one of the best article we published. Okay, so that means it takes time to identify the model which is able to reproduce experimental data. Physicochemical property is very easy, but biological activity is more complex. Okay, so don't try to expect too much from the biological activity context. So if you don't publish, it is good compared to publishing something fake or wrong results. Okay, so it takes time. You should have patience to understand the chemical relation with respect to biological activity. This point is very, very important. Okay, so don't be in hurry to build a model which predict for some particular class of compound or particular diseases. So there is one more thing here we have to talk about. One is called application domain, applicability domain, where your model is applicable. Suppose if I build a model which predict which I use the data for melting point prediction 14 degree to 450 degrees Celsius, and then if the model predict beyond 400 degrees Celsius, that is not reliable. So your reliability depends upon what range of data you took, what range the bioactivity range, what type of disease you took, what type of compound you took, whether how much diversity is there within the molecule. There are several factors to be considered to depend upon which model is reliable. Computer throw any data, but which one is good, which one is reliable, which one is reproducible. This is very, very important factor. For that, you should follow certain protocols. So this itself is a 3 hours lecture. It is very unfortunate that physically I'm not there. Otherwise, I can give a lecture on how to build a QSAR model, how to validate, how to correlate, how to find the relationship between experimental versus predicted value, how much variation should be there, what is outlier. There are several things are there. This itself can be a 6 months course. We actually conduct the practical chemoinformatics course in National Chemical Laboratory under ACSR program. We teach all these things. Even if we teach at other universities like NIPER. So students should know, given a value of molecule and bioactivity, how they build the QSAR models. A lot of data is available, but they should practically should do it. Okay, so today very few universities are teaching a hands-on session on how to build the QSAR models. It is a must for each and every faculty member and also for the students. Okay, then you can find the correlation between experimental versus predicted value. AI should tell you which is the most accurate model you are able to do. At the end of the day, you built the virtual library of compound of your interest, and then you already built the QSAR model. If the compound is not good, it goes to the trash because the model predicts not active, so it goes to the trash. If the compound is predicted to be active, then you can talk to the synthetic chemist. You can tell that I built a QSAR model, this compound is potentially biologically active, can you synthesize? Then maybe he will consider, because he knows that he rejected so many compounds. So out of 100 compounds he planned, only 10 passed the test. So the 10 compounds it can be prioritized for synthesis, and that can, out of that synthesis, so whatever is synthesized can be go for biological screening. So you can also study how relevant your molecule in a chemical space, in a biological space. So much data is available. You can find the molecular diversity analysis. You can do the screening process. You find the so many filters are there. For example, chemo filter, toxico filter, pharmaco filter. Once you apply this filter for the compound, finally you can go for synthesis. So I think I have 10 more minutes. I will go into the practical session. So then basically we have chemo force. We have to calculate the chemo force for the anti-cancer context. What are the functional group responsible for anti-cancer activity? This peak will tell out of 30 compounds, 25 compounds are having these features. There are only 5 compounds are having this type of features. So which features are mostly important in cancer context, which features are less important, which is very less occurred, and then the more occurred, the longer the peak. Okay, then you can find the toxic compound versus biologically active compound by doing self-organizing map analysis. Then you can find the relationship between biological activity and the similarity. Then you can find the similarity, then you can pick up the compounds from this huge similarity and dissimilarity score. So we actually published all the details which I presented here in several journal articles. Basically, once you have these molecules, then you can screen against particular target of interest with respect to cancers. So next 5 minutes, actually, what we developed takes long time to explain, but lack of time, in next 5 minutes, we put all the theory which I told you in one computer software tool as part of our ongoing research program. It is highly funded by our CSIR. Okay, so the CSIR funded the development of a tool called Compute Cure Cancer Toolkit, which was funded in 2018, and it was concluded in 2020. In 2 years, we developed a toolkit using open source tools, but because of the COVID, we could not progress much, and we are waiting for the next phase of funding where this phase 2 will go, where we integrated several tools: data mining tool, big data analytic tool, machine learning, deep learning, bioinformatics, sequence alignment, even patent mining with respect to cancer, literature mining on cancer. And then there are about 1,30,000 publications are there on cancer. You can go back and check in PubMed. So there are 1,30,000 or 1,40,000 publications are there in cancer. Now you can use this tool to harvest the chemical information with respect to cancer. Okay, then this all the tools which I'm mentioning, QSAR, QSPR, etc., is already integrated in the tool. Then we took this data which I mentioned that there are open source data is available. There are about 3 million data points we extracted from the public domain with respect to cancer, CNS, colon, breast cancer, all type of 10 type of cancer. Then we got about 4 GB of molecule and bioactivity relation data. These data went to the machine learning, deep learning, artificial intelligence toolkits to build the models, which I already explained to you. Then we used the machine learning methods like PLS, KNN, random forest, decision tree, multilinear regression, support vector regression. Okay, then RNN, then LSTM, GRU. These last 3 things are deep learning methods. Okay, then these are the 10 type of cancers. There's 7 type of machine learning, 3 type of deep learning. We built the several models. We are able to now predict the bioactivity or anti-cancer activity for a given molecule for all 10 type of cancer using all 10 type of models. Okay, so please understand, this is the 100 models built using 10 types of modeling and 10 type of cancer. So for a given molecule, I will be able to predict 100 numbers. What the 100 number represent? That 100 number represent the bioactivity of the compound with respect to cancer using all type of methods. That's all. So now you have a these are the whatever is the dark spots here shown as a training things. What is the small dots or compound which is not yet synthesized or reported? So these are the virtual compounds. The small dots are virtual compound. The dark dots are these 3 million experimental data points, which I discussed, that already publicly available domain, where uh, all the molecule and the corresponding bioactivity is already available. What is the dark spot? Now, using this one as a seed, you are able to find out the bioactivity of unknown compounds. So what is the procedure? You have a chemical structure, you have a molecular descriptor or intrinsic properties, and then you build the AI models, MLDL models, and then you are use the virtual screening to inactive versus active. Then you pass through the procedure, you go through, you need huge computing power for doing this, and then apply the model. You have a training set, test set, so you external validation set, then your observed value versus predicted value, and you find out where this model did not fit or the molecular something different. Sometimes it is not necessary that all the molecule will obey the model. So whatever it predicts, maybe there is a internal complexity of atomic combinations responsible for the molecule is not behaving as we expected. Okay, then once you have the model, once you have reliable model, then apply this model on virtual library, then you predict the bioactivity. This is where you get the novel molecules which you can patenting, etc. So in summary, you have a cancer types, you have a bioactivity, you built the n log GI50 for clinical drugs. So then what is the use of this? Now you go to the all the clinical drugs used in cancer, try to find the similarity between them, and what is the factors responsible for these clinical drugs as a clinical drug for treating cancer on specificity of particular cancer. Similarly, you apply the same machine learning, deep learning method. Now you will be able to predict the drug like anti-cancer drug like compound with respect to breast cancer anti-cancer drug like compound, colon cancer drug anti-cancer compound. Like this, you can design based on the procedure which I explained to you. Then I don't want to go into details. It's a very complex components are there in the software. So we put the huge data into the system, then we put the intrinsic property calculations, and we applied the same technology for procedure is same, whether it's the anti-cancer or antiviral. So we took 50,000 compounds from chemical abstract service. They generously given all the antiviral like compounds, and then we use the same procedure for with respect to COVID. Okay, so the molecular descriptors varies. Then Lipinski rule of 5, where there are some rules are there, 4 rules are there, whether the compound is drug like or not. Here we are talking about 200 descriptors. Maybe it can be called 200 rule of anti-cancer agents. Okay, I don't want to name it. Okay, so it's up to you. So they used 4 characteristics, then it's called Lipinski rule. Here we have 200 features of a molecule responsible for anti-cancer activity or antiviral activity. What is the variation in chemical structure responsible for anti-cancer activity and antiviral activity? These are all integrated in the software. So once it is second phase is established in the project, and once it is published, once it is patented, it can be made public domain. Everybody can take the code, they can practice, they can modify, they can upgrade, and then again they can publish. Okay, so this is the preview. I will skip some of the things. The huge 3 million data points is already integrated in the system. You can see the variation in IC50 values for every compound, how the same compound varies response with respect to different type of cell lines. Okay, you can see the breast cancer cell line, then CNS cancer cell lines, colon cancer cell line. So the first each row represent molecular response with respect to cell line activity. Then this also can be shown as a your heat map. Okay, you can see which compound is promiscuous. Promiscuous means it has a same activity against all panels. Where is something selectivity versus promiscuity? You should know all these things. You can study all these parameters. This is developed in 2017, and it is being upgraded daily basis. Okay, we're continuously working on it. This toolkit as handling the targets, it handles the molecules, it handles the large collection of molecules, then sequences, gene informations, all type of machine learning, deep learning techniques are integrated in the system. So you have to just upload the molecule which you found in medicinal chemistry journals, and then try to predict the then extract the molecular scaffolds, build the virtual library, scaffold and functional group you extract, and build the huge virtual library for the compound which you found from the literature, then it predicts the bioactivity. So like progressive drug like score, lead like score, etc., etc. So now you can also predict anti-cancer activity with respect to particular disease, maybe anti-cancer breast cancer, anti-breast cancer activity, anti-colon cancer activity, using different type of methods. So you will be able to get a huge data. Once you get the data, then you can analyze which compound is with the virtual library of novel molecules, which one is likely to be more potent against breast cancer on that particular cell line. Up to that level you can go. So we have a huge cluster of computing resources to do the task. Right now, because of the COVID, so many activities are paused. Eventually, in another couple of months, we'll be able to start again once the funding comes. So then we are able to do the everything in a background. Just click one button, it will do all the identification of PDB with respect to cancer type and molecules, etc. You can do molecular visualization, 2D, 3D. You can do docking studies automatically. Once the compound which is shortlisted using QSAR, it will go for docking studies within the system. And then you can see the binding affinity for the molecule with respect to target of interest. Then finally, you can prioritize. So in this COVID, target and viral ligand 1. So you can see among these, which one is better, you can find. So you can say that compound 2, ligand 2 against 6W75 viral compound has a better binding affinity. Okay, so like this you can shortlist. Everything is automated. Now you can also shortlist the binding energy plot. Okay, so these are all automatically integrated, and all the cluster of computers are used for identifying the ligand interaction with the receptor of interest, whether it is anti-cancer, antiviral, etc. Now you are able to do it automatically. So this type of freedom is not there in commercial software. So this software is able to do text mining, data mining, extracting the information, uh, etc. Okay. So this type of actually people publish in the journal, and which is not reusable format. So we have to develop a PDF text, PDF to text, and then text to table, table to machine learning. It's a very complex procedure. So here I will spend another 2 minutes with the permission of the coordinator. Uh, so to complete the how you can do it yourself from the beginning.
Sir, you can continue, sir. No problem.
5 more minutes. Okay.
Yes, sir,
maximum
yes.
by 1:15 we will conclude the presentation. Okay.
Yes.
Since you have so much patience, only please 5 more minutes, very critical. How you can start doing antiviral drug discovery. So you have access to SciFinder. Go to SciFinder, search for this. I am interested in antiviral agent for COVID-19. That is my query to SciFinder. So it is mentioned here. Research topic is antiviral agent COVID-19. So you go to SciFinder, then you found 117 references with respect to antiviral agent of COVID-19. So the next step is it is in the patent space, I think. Okay. So then you start extracting the identifying the, now you again go find the substances related to my anti-COVID activity. Especially I'm interested in adverse effect, biological studies, preparation process, etc. Then you get all the details. Then you get the chemical structures. In this process, you don't need to draw a single molecule. Okay, to draw molecules of complexity like this, it takes so much time in ChemDraw and other softwares. But here, the easiest route is go to SciFinder, search the compound, download the molecules, and then you extract the things. Now you got the 64 substances selected by doing filtering several methods, because you are interested in property, biological activity, preparation. So there are 64 molecules you found. Then you found what are the frequent hit antiviral scaffolds. So out of 64 molecules, you found these are the 6 scaffolds most frequently occurred. So you can this program we developed for NIPER Kolkata, where now you put all the scaffolds into the system. Once you have the scaffolds, you can build the virtual library of molecules, and then you can calculate the molecular descriptor. You have a list of compound, known compound. You have there are about 88 entries of known antiviral compounds, and then it is calculated intrinsic properties or descriptors that is used for building the mathematical model. Now you can predict the antiviral activity for these compounds. This is a standard procedure. Okay, so I just demonstrated that from SciFinder how to extract the data and how to use it in your conventional or both commercial and open source tools to predict the bioactivity. Okay, if someone is interested, please contact me. Maybe with some MOU we will be able to implement, test it in your system, but only requirement is you need to have a Chemaxon license to run the software. Okay, so our software is also needs to be processed before sharing with other universities or institutions, but in a collaboration we can do it that easily. So as I said earlier, so we extended this for high throughput screening. Once you identified that these are the anti-cancer agents, how to synthesize that? These are the novel anti-cancer agents, so we are using this AI for synthesis planning. So in 1993 we talked about few chemical reactions, maybe some 50 chemical reactions. Today we are handling 3 million chemical reaction which is present in the patent space. So we downloaded, analyzed, now we know how to synthesize a compound from a given molecular structures. So we use high performance computing to do that. You can see that we are using 384 processors, 100% active. Still we need more computing power. So we taken all the we converted all the technology which I presented here in the patent format. So today you don't need to even have software. If the software is implemented in Amazon or some other cluster or NCL cluster, you send one email saying that how to send an email, and then the robot will do the um, uh, docking studies, QSAR studies, and it will throw. So what you have to send to the email? You have to send the email 1 HIV, comma, aspirin as a subject line, and then to remotecompute@gmail.com. Then what it will do? It will convert your 1 HIV into a protein target, because it should be 4 character, and then aspirin is a molecule. So it extracts the 1 HIV from the PDB database, and then it downloads the PDB. Then aspirin, it converts name to structure, structure to 2D, 2D to 3D, and then if the target is available, download the PDB, and then do the docking studies, and then binding affinity is calculated. Then that become your target, your confirmation molecule, bioactivity, everything calculated things will go to the your Dropbox. So that data will be stored in the Dropbox, and the link will be sent back to you by email. So you send the email 1 HIV aspirin, you get a link containing complete zip file containing all the target bioactivity, predicted bioactivity, and your binding energy profile, confirmation of the aspirin in the active space. So this we have taken a patent. We demonstrated docking studies, QSAR studies, virtual library, text mining in the US granted patent. And then today I am talking to you last 2 hours about drug discovery. Imagine in future, in 2050, by the time I complete my presentation, Alexa or some Siri or some other software will extract the chemical structure from my slides, and then it can do the calculations in the back end. Maybe it will send it to registered pharmaceutical companies. Okay, so AI can go up to that level. It can recognize the chemical structure from the screen, convert the screen structure into a truly computable chemical structure, then it can do QSA or docking studies or any property calculations. Okay, that is much that AI is listening today. Alexa, play this song. Alexa, tell me the story. Similarly, in future, you can say that Alexa, design a COVID drug. Alexa, design a new breast cancer anti-cancer agents. Maybe it is possible 2050. In future, people are talking about brain-computer interface. You don't need to even speak to the computer. You just think with some helmet or some embedded chips, then your data will be communicated properly. So uh, suppose this is what I was trying to tell you, that as we send the email and the docking is done, in future the computer will see the things on the Zoom presentation or your Google's presentation, and maybe it will start designing the new molecule. So there is a threat possible when you talk the Zoom and other Google Meet presentation sharing. Okay, so it is listening. Okay, so Alexa listening. So Alexa is able, means these machines are now very smart enough to recognize the car, people. Why not molecule? Why not bioactivity? Okay, so this I think last time also I spoke that by the time I complete my talk, Alexa would have developed a new drug. Okay, So that is not very far off from today. And the technology is today possible. Whatever the technology which I explained to you, if it is integrated with Alexa, it will be able to convert your image into molecule, molecule into descriptor, descriptor into 2D, 3D, and then it can process the QSIR, and then it throw the data to the open storage spaces like your Google Drive or Dropbox, and send the link to your email. Okay, so trust but verify. The risk is there, but you don't worry, it may be used for good purpose. Okay, so anyway, traditionally teacher used to watch whether how you are writing exams. In future there will be web camera that will tell you, or today online teaching, online exams going on, so it will be able to do it in future. So in conclusion, whatever I presented today is already available in the textbook format, and we also published all the work in the journal article also, back to back, all type of studies. These are all continuous publications in the 2 issues which I mentioned. Okay, then we this also I mentioned that send an email and then harvesting chemical information PDF document. Give you a PDF file, for example, your medicinal chemistry journal article, JMC article PDF file. You give it to the computer, it will extract all the molecules, it will do the docking and QSR studies, just giving PDF as a input without drawing a single molecule. So this type of studies also we have taken a patent recently. It is granted last year. So we are able to do the PDF to drug discovery. And then we also work on huge in Ayurvedic context, how to discover novel drug molecule from the text mining of literature to find out the metabolomic analysis of Indian medicinal aromatic plants. So I want to skip that. Please go through this article. There are 17 goals. Okay, so this is, you spoke, you had so much passions. Now in the conclusion, can you recognize who is the lady? I can give you $1 million. You may think that, sir, how you can give $1 million? This is a reward, for example. Okay, if you can't recognize her, I will show another picture. 1 million reward. Did you ever seen this lady or child? Did you ever seen this girl? Again, $1 million. Did you see this boy? Again, $1 million. Okay. So you lost $6 million because you could not recognize any of them. Okay. Again, I repeat, 1, 2, 3, 4, 5. Okay. So you lost $5 million because none of the participants, 30 participants are there. Everybody lost $5 million because I shown you could not recognize any one of them. You can recognize my photo now, but you could not recognize any one of them. I can tell you, these are all fake photos generated by AI. Okay, these are all the fake people who doesn't exist. Okay, so computer generated images, can you believe? So why not a drug of interest? You just think about it. AI is going somewhere very far. So these are all available. This person does not exist.com. So that AI generated photos are being made. Okay. Okay. So this is a final but one slide. This is a motivational for all the participants and teachers and students. Thinking is easy, acting is difficult. To put one thoughts into action is most difficult thing in the world. The ultimate measure of the man is not where he stands at the moment of comfort and convenience, but where he stands at the time of challenge and controversy. And please remember, don't run behind Nobel Prize, awards, Bhatnagar, Bharat Ratna, etc. The true reward of honest work are neither be seen or nor handled, nor measured by gold standard or by any material result. They are not acclaimed by the applause of the crowd. It lies within you, in your best knowledge, that you have done your best, that you have striven to reach your own standard of highest power. You will often fail, often, perhaps always fail, to reach your own ideals, but comforted ideals are not for attainment, but the pursuit. So with this point, I like to thank. So my motivation is, when I was in defense, I used to interact with Dr. Kalam. That motivated me. And then actually, this is the last slide. This presentation is dedicated to my parents, and especially my today Father's Day. I won't be presenting if my father would not have allowed me to continue my research. I was a school first in 10th standard. So my father could not stop me pursuing my studies because he felt, अच्छा पढ़ रहा है पढ़ने दो, ठीक है? So that helped me, even though we are coming from a very humble background. My father allowed me to study without his support. I studied from government school. I studied from local language school. It was very hard for us that time. I'm talking about 1980s. Okay, so without his support, today I would not have been here talking to you. There are so many fathers, so many parents are here. You may be a father, you may be a child. So this is the day you have to go look back and say thank you to all. Okay, as a father, you get the congratulations from your children, but you should remember your parents. Because of that we are all here. Okay, happy Father's Day. Thank you. If you have any questions, please unmute yourself and I will check the chat box also. Thank you, Raja Ramji. I think I presented it. Thank you so much.
Thank you, sir.
Let me see the question.
Sir, we have received some questions from chat box.
Yeah, I'm seeing louder, but I see. Bimalandu Chaudhary, please. Whether AI can helpful in designing novel molecule having lesser adverse effect? I think I covered it. Is there any relation between AI and computer-aided drug discovery? I think that is also covered, the procedure in which I shown you. And dear participant, sir, please show how to improve existing data related to biological property without using animal model. Okay, the Bimala Tripathi. Okay, that we can see. Can AI helpful in designing an anti-cancer drug effect on targeted cells? Yes, we discussed. Okay, sir, is there any free software available on AI? That was the first part of my presentation. I listed all the softwares. You go through the publications which I mentioned. If it is recorded video, you can go back. Some of the slides I can share with you. So, Dr. Anyone has a question or doubt? I think I answered most of the questions. Still, if you are not convinced, please unmute yourself and we can have one question or two questions. My email ID, phone number is given here. So phone is not possible, but email you can send it to me, especially Gmail, because office mail, sometimes I don't get the things.
Any participants, any questions?
At least you tell me whether you understood or not. None of them you understood. Everything you understood. If there is no question, there is only two reasons. One, you understood everything. Two, you did not understand anything.
It is very clear, sir, and it will be very useful for the faculty members. And you have given insight to the theory and practical based artificial intelligence and its applications. So it will be very useful for us, sir. Thank you once again, sir.
Thank you so much.
Rajaram, sir, you can proceed.
Sir. Thank you so much, Dr. Karthikeyan, sir, for a nice and informative session on chemoinformatics and AI. All our faculty friends are going to be highly benefited by going through the facts and figures illustrated today. The entire session was too lively, engaging, and educative because of your presence, sir. Thank you once again, sir.
Thank you so much for giving opportunity.
Thank you, sir.
I wish you happy.
May I request our beloved principal, Dr. BVP Ravi Kumar, sir, to felicitate our venerated resource person, Dr. M. Karthikeyan, sir, with an e-certificate of appreciation as a badge of our deepest sense of gratitude and respect from the entire pharmacy faculty fraternity.
Thank you, Dr. Karthikeyan, for giving valuable information about the use of AI in drug discovery. We would like to have you in future also with some more advancements in this area. Thank you on behalf of all the delegates and on behalf of the management and all the participants present here, I would like to present this e-certificate of appreciation. Please accept it, sir.
Oh, thank you. But I also have one request. Once the COVID is over, I will physically visit and meet the faculties who attended the lecture, and I want to see their action plan from today.
It's our pleasure, sir. It's a great idea. Thank you, sir.
Thank you so much.
Thank you once again.
Thank you. Can I disconnect now?
Yes, sir.
Finally, I would like to take this opportunity on behalf of entire organizing committee, Roland Institute of Pharmaceutical Sciences, to place on record our hearty thanks to Honorable Vice Chancellor Sir, BPUT, Director Curriculum Development, BPUT, Dean Pharmacy, Directors and Principals of all BPUT affiliated colleges. Above all, resource person of today's event, Dr. M. Karthikeyan Sir, for sparing their valuable time for us. We are really enlightened with their knowledge and presence. We are thankful to our Honorable Management Committee, Roland Institute of Pharmaceutical Sciences, for their constant support, motivation in all dimensions to carry out such kind of programs. I would like to thank our principal, Dr. Professor B.V. Ravikumar Sir, for his enthusiastic support throughout the program. A special thanks to the program coordinator of this event, Dr. Bisumon Sahu Sir, for the timely arrangement and his precise efforts for the smooth conduction of this event. My special gratitude to all members of the organizing committee, teaching and non-teaching staffs, and the faculty delegate friends for their unflinching support and coordination. With these warm words and kind messages from our eminent personals, we now officially conclude the second online faculty development and training program on chemoinformatics and AI for anti-cancer and antiviral drug design. I wish this FDTP a resounding success. Thank you very much, all the faculty delegates, for sparing your valuable time and your kind cooperation. Thank you all once again. Thank you very much, sir.